Hello, my dear students. Welcome back. We're going to continue today with signal transduction part 2. But before we get started, let's have a little review of what we did last time before we continue. Okay, this is where we stopped last time. We're trying to figure out how a heart cell is activated or stimulated by the beta 1 adrenergic receptor. Okay, so let's zoom in here. Well, let's just do this first. Shown here is a heart cell. This is a heart cell here in black. And what happens? Epinephrine, which is our ligand, binds to the beta 1 adrenergic receptor. And then a series of events take place that lead to greater contraction of our heart cells. And so what we're going to do during this lecture is figure out what are those biochemical steps. What is that biochemical pathway that leads to activation and contraction of these heart cells? Okay. Last time, let's just catch up with where we were last time. So here we have epinephrine binds to the beta 1 adrenergic receptor. When epinephrine binds to this receptor, here, then this receptor is activated. And once it's activated, then a protein comes in. Okay, let's just grab this protein here. Let's see if it allows us to grab it. This protein, this trimeric protein, comes in and associates with that receptor. Then this protein itself becomes activated. This protein is called the G protein. It becomes activated, and it loses GDP and gains GTP. So we're going to move this GDP out of the way, GDP protein out of the way, and now it gains GTP. And you can think about it this way. GTP has lots of energy. GTP has more energy. So this protein is now activated because if you think about it, adenosine triphosphate has more energy than adenosine diphosphate. In a like manner, guanosine triphosphate has more energy than guanosine diphosphate. And so now we have our activated G protein. And so what's going to happen next is this G protein is going to dissociate. We're going to have G alpha is going to dissociate by itself with the GTP, and G stimulatory beta and G stimulatory gamma are going to move away. And so this is the situation we're left with. The G stimulatory beta and alpha dissociate from G alpha, and now we're left with, let's see if I have these two together. Hope I do. Yes. And now we have activated G stimulatory alpha. Now G stimulatory alpha now moves to another protein in the membrane, and it activates. It binds to that protein, and it activates that protein. And this is where we stopped last. And we said one other thing. This protein, the job of this protein is to turn ATP into cyclic AMP. So this molecule here, I don't know if I should have to write it. I shouldn't have to write this because it should kind of make sense. Let's see here. Okay, but I'll put the name of it. Okay, yeah, some of you all were. Okay. This protein, the protein that's activated by G stimulatory alpha, the protein that's activated by G stimulatory alpha, this protein here, this protein converts ATP into cyclic AMP. And the whole point of all of this is we're trying to get the heart cell to contract more. It contracts by itself. I mean, you don't need a beta adrenergic receptor for the heart to contract, but if you want a stronger contraction, like if a dog is after you, that's why you need epinephrine to do that. Make sense? Very good. So here we have ATP is converted to cyclic AMP. And so I'm going to put the name of this here. Okay, so this molecule here is cyclic AMP. Cyclic AMP. That's what the C stands for. CAMP, cyclic AMP. Okay. Everyone with us so far? Things make sense so far. Now what we have to do, before we continue this signal transduction cascade, we need to name this protein. We need to name this protein. So this protein, what does this protein do? What is the job of this protein? It converts ATP to cyclic AMP. So what if we had to just make up a name for this protein? If we just had to make up a name for this protein, what would be a good name to give it? If you were the person who had to come up with the name of this protein, what would you call it? Okay, ATP converter, but it cyclizes the ATP, so it has to have, what's it now? It could be C protein, right? Okay, CATP. Those are all good names, But the main point of this protein is that it cyclizes the adenosine. And so we call this protein, it's kind of a strange name, but we call it adenylyl Right, this is that big protein. It's called adenylyl cyclase. It takes the adenine or the adenosine nucleotide and cyclizes it. And so that protein is called adenylyl cyclase. Make sense? Question? Have a question? Make sense? Okay, adenylyl cyclase. That's where we are now. Okay, so when scientists first started looking at epinephrine, they would take a heart or a heart cell or even a heart, and they would drop epinephrine onto that heart, or they would inject that heart with epinephrine, and then the heart would start beating more strongly and it would start beating faster. They say, what's going on here? What's going on? And then they decided, let's do this then. Let's just take a heart cell, add some epinephrine to it, and then see what chemicals change their concentration inside that cell. What chemicals increase their concentration and what chemicals decrease their concentration. So now I have a question for you. When they did these early studies and they took heart cells, they added epinephrine to these heart cells. And then they looked in the cell to see what chemicals increased in that cell. What chemical do you think increased its concentration? Exactly. Say that again. Cyclic AMP. Doesn't that make sense? You're going to have, if you add epinephrine to a heart cell, you're going to get an elevation in the level of cyclic AMP. What chemical is going to decrease in the cell? ATP. Make sense? Yes. Question. Exactly, but in a cyclic form. Exactly. Exactly. Okay, the question is, the cyclic AMP, is that adenosine monophosphate? That was the question. And my answer was yes, but it's just simply in a cyclic form. And the second question is that when it loses its phosphate during this conversion? And the answer is yes. And it takes energy to do that conversion. That's why that phosphoanhydride bond is broken. You break that bond and you create pyrophosphate and cyclic AMP. Let me just show you something quick. very quickly here. I'm going to get rid of all of this for just 1 second. Okay. If you have, here we're going to have, this was going to represent adenine. So this is adenine, and attached to adenine, you're going to have our phosphates. Well, I'm going to make it real simple now. I'm just going to put phosphate, phosphate, phosphate. And so this molecule would be, this would be ATP. And so this is ATP here. And so when adenylyl cyclase comes in, the enzyme adenylyl cyclase comes in, then you're going to end up with your adenine, and then you're going to have your phosphate here, and then your phosphate is going to attach to adenosine again. And so it makes a circle. The phosphate makes a circle. And so that's why we call it adenylyl cyclase. And so this would be cyclic AMP. And again, I'm drawing it in a very crude form just so you can understand the concept. We'll look at the actual structures later. But so you cycle that phosphate. See, phosphates look like this. And so that's how phosphates look. And so if this is adenosine here, and again, I don't want to get too detailed, it will bind adenosine in 2 places. And so it makes a little cycle out of it, a circle out of it. And that's why it's called adenylyl cyclase. Okay. That may kind of make sense? Okay, we'll talk about that. Good questions. Excellent questions. Okay, now, scientists came up, during these early studies, they came up with this term to describe the chemical that increases concentration inside the cell. And so what they said, okay, if we add epinephrine, it would be like me saying, let's see here. It would be like me saying, okay, I'm going to tell Shelby something, and I want Shelby to give that message to Shaw. Okay? And so I would be the first messenger, or I would be the first messenger because I would give the message to Shelby, and then Shelby would be the second messenger. Now in this situation here, so scientists got epinephrine, they added epinephrine to heart cells. So epinephrine would then be the first messenger. Okay? And then what would be then the second messenger in this signal transduction cascade? What would continue? What molecule is going to be responsible for continuing our message now? No.
The AC?
No. Only one more left. CAMP, exactly. Cyclic AMP. Now we know now that, well, cyclic AMP shouldn't be the second messenger. If we think about it now, we would say, well, the G protein should be the second messenger. Or we could say adenylyl cyclase should be the second messenger. But when they did these early studies, they didn't know how to measure. They couldn't measure GTP because they couldn't measure the G proteins level because it doesn't change. And they didn't know how to measure that anyway during those early studies. And adenylyl cyclase, its activity increased, but during these early studies, they didn't know how to measure. They didn't know how to measure that. The only thing they knew is if you add epinephrine to a heart cell, you're going to get an increase in cyclic AMP, and so they call cyclic AMP the second messenger. When in actuality, it's kind of like third in the list. Does that make sense? Okay, so cyclic AMP is called the second messenger, and we're going to talk a lot in signal transduction. We're going to make a lot of references to second messengers. So cyclic AMP in this situation, let me make sure. I think I added something here. What is this? Okay, we don't need that. So in this situation, cyclic AMP is the second messenger. That's going to be kind of an important concept that you understand, the second messenger. Okay? Okay, and so that's where we are. We've gone from epinephrine to our second messenger, cyclic AMP. We still don't have contraction, so we have to go farther. What happens next? I should do this part first. I'm going to do something else first here. Now, the G-stimulatory protein, has GTP associated with it. And so what it's going to do, it's going to, once one epinephrine binds, it's going to stay activated for quite a while. And it's going to keep on activating adenylyl cyclase. It's going to tell that protein, okay, make more cyclic AMP, make more cyclic AMP. But eventually, epinephrine is going to be degraded, it's going to be gone, and it's going to continue to tell adenylyl cyclase, make more cyclic AMP. But you don't want if a dog is running after you, and you run away from the dog and you're away from that situation, you don't want that G-stimulatory to stay on all of the time. You want it to eventually turn off so that your heart rate can go down, because if your heart rate just stays up, then you're going to get ischemia, and then you're going to have a heart attack, and then you're going to die, and the dog won't even be there. So you don't want that to happen. Make sense? Okay, so what you want, what this G-stimulatory protein has, it has on it a hydrolase that breaks down the GTP back to GDP. And now there's no exchange that takes place like in the first situation. It actually hydrolyzes your GTP. So what's going to happen? This protein here, the G-stimulatory alpha subunit, has GTPase activity, its own intrinsic GTPase activity. And what it does, it converts itself into, should I draw this over? I'm going to have to because I don't see it anywhere. Okay, it converts itself into, let's see if I can just grab this. You all can't do this, but I can. Okay. It converts itself back into this form. I'm going to erase this here. Converts itself back into GDP. And now when it converts itself back into GDP, now adenylyl cyclase can turn itself off. And it doesn't continue to make more and more cyclic AMP. So that your heart rate will eventually go back down to normal. Everyone okay with that? Now what's going to happen? The G-stimulatory alpha with GDP is going to now join back with its friends, G-stimulatory beta and G-stimulatory gamma. Now they're just going to wait around until more epinephrine binds to the beta-1 adrenergic receptor, and the whole process starts over again. Question? Mm-hmm. Okay. The G-stimulatory alpha has an enzymatic activity on it that clips off one of the phosphates to turn it to GDP. And that activity is called GTPase activity. It's a guanosine triphosphatase activity because it takes away a phosphate. And so we call that activity GTPase activity. So this is the intrinsic GTPase. GTP into GDP, because you need a way to actually turn that protein back off. You have to turn it off, because if you don't turn it off, it's going to stay active forever. And you're going to start making too much cyclic AMP, or the cyclic AMP levels will stay high too long, and your heart will beat fast and hard too long, and that'll give you a heart attack. GTPase. GTPase. That's the intrinsic activity. So this G stimulatory alpha can do two things. One side of it can activate adenylyl cyclase, and one side of it can chop off the phosphate to deactivate itself. So if you have a GTPase that stays active a long time, that can give you a really high heart rate, but it can be bad. But if it's too short, then epinephrine wouldn't do its job. It's called GTPase activity. So this GTPase stimulates the cell, stimulates the protein to cause stimulation of the cell. Have I lost anyone yet? Are things questioned? Okay, now let's go back here. So here we have G stimulatory alpha with GTP. It activates adenylyl cyclase. Now it gets to the point where you don't need it anymore. So that intrinsic GTPase activity of the G stimulatory alpha is going to convert this GTP to GDP. Okay, you got that step. Now what's going to happen? I think I have this attached to this. Let me dissociate this because I put all of this on the same. Okay, make sure I have the right one. Okay, so now what's going to happen? This G stimulatory alpha GDP is now going to go back and associate with G stimulatory beta and gamma. Remember, that's who it was with before. At the very beginning, that's who G stimulatory alpha was with. It was with beta and gamma. And now we're back at the point where we started before. Okay? And here is, well, this is our epinephrine here. And so now when epinephrine binds again, now the beta-1 adrenergic receptor is going to be activated. Now all three of these are going to go to the membrane. And now you're going to, well, let's just do it all over again. But these three are together, so I'm going to have to link these together. Here and, where is that other one? This one and, see if I can find them. Remember 42 and 49. Okay. So I'm going to put these two together because I need them to be together for right now. Okay. So when the beta-1 adrenergic receptor is activated, this is the whole process again. All of this is going to go to the receptor and bind to the receptor. Now GDP is going to be exchanged for GTP. And so now what you're going to do, you're going to lose the GDP, and then the GTP is going to replace it. Now the GTP, G stimulatory alpha with GTP, is activated. So now what's going to happen? Once G stimulatory alpha becomes activated, it's going to lose beta and gamma. Beta and gamma are going to go away. Now G stimulatory alpha, GTP, is going to go and activate adenylyl cyclase. Now adenylyl cyclase is activated. It's going to convert ATP into cyclic AMP. But now let's say epinephrine goes away. It's not bound anymore. You don't want this to continue to activate adenylyl cyclase. So the intrinsic GTPase activity on G stimulatory alpha is going to convert G stimulatory alpha GTP into G stimulatory alpha GDP. Now it's inactivated. Now what's going to happen? Now the G stimulatory alpha GDP is going to go and join back with its friends, G stimulatory beta and gamma. Now the three of them are just going to wait again for epinephrine to come back. Now something stressful happens to you, then epinephrine is going to bind, then the process starts over again. Make sense? So that's how you get more cyclic AMP. And that cyclic AMP is going to eventually lead to a higher heart rate and a stronger heartbeat. Everyone with me so far before we continue? So now we're at our second messenger, cyclic AMP. Now let's continue. Okay. So what I'm going to do, I'm going to make this heart. Let me see if I can grab this. Some of this I can't grab. I actually have to, but I don't want to get rid of it. I'm just going to grab this part here because I need a little more room here. So I'm going to just grab this, our contractile units here. Okay. So I'm going to make this smaller here. These are our contractile units. I'm going to make this a little smaller. We may make it bigger later, but for now we need it to be small. Let's do something here. Okay, now we have cyclic AMP. Let's continue. Now cyclic AMP is going to now, let's go here. Cyclic AMP is going to now go to another protein. We won't put the name yet. It's going to go and activate another protein. And what this protein does in a heart cell, you have these channels in the heart cell. Okay. You have these channels in the heart cell, and what these channels do, they open up and they let, let's get a good color here. They open up and they let this ion go into the cell. So this ion then floods the cell. What ion is this? Calcium, exactly. But normally, under normal circumstances, this channel is not open. What happens, this protein here adds phosphates to this channel. And when you add phosphates to this channel, that opens this channel up.
Does that channel lead to the outside of the heart? What's that black one?
This is the inside of the heart cell. Right, and this is the outside of the heart cell. And so when this channel opens up, you let more calcium ions into the heart cell. Now we have to give a name to this protein. Well, let me ask you all something. Let's go back up here. What is the name of a protein that cuts off a phosphate, that takes a phosphate away from something? What was that? No. Yeah, it ends with ACE. What's the name of a protein that takes away a phosphate? Yes, GTPase. What does P stand for in phosphate? So a protein that takes away a phosphate is a phosphatase. Make sense? You take away a phosphate, you're a phosphatase. Now, this is the tough question. Now, this protein here actually adds phosphates to this calcium channel. Let's go ahead and put here, this is a calcium channel here. Here we have a calcium channel. This blue protein here actually adds a phosphate to the calcium channels to open the calcium channels up. Now, this is a general question. What is the name of a protein that adds a phosphate to other proteins, or that phosphorylates proteins? So the name of a protein that takes a phosphate away is called a phosphatase. What's the name of a protein that adds a phosphate? This is a tough one. There's no way you can know this unless you're like a genius or something. We call this protein we call such a protein a kinase. Why? Why is it called a kinase? I don't know. But it's called a kinase. Kinase. So kinases add phosphates. Phosphatases take them away. And that's something you'll have to remember. You have to remember that for the future. Yes, that little blue protein is a kinase. We haven't given you the specific name of that kinase, but it is a kinase. Okay. Scientists decided, well, since this protein, it is a protein kinase because it's it's phosphorylating another protein. So we call this a protein kinase. And scientists said, well, let's just call this protein kinase something. And since it's activated by cyclic AMP, they decided to call this protein kinase A. So this protein is protein kinase A. A protein kinase because it phosphorylates a protein, A because it is activated by cyclic AMP. Now later on, when we look at other signal transduction cascades, we'll talk about protein kinase G. What do you think activates protein kinase G? What activates protein kinase A? Cyclic AMP. So what would you think activated protein kinase G? Cyclic GMP, and we'll talk about that when we talk about smooth muscle contraction and penile erection. We'll talk about those. Those are involved in those cascades. Let's see here. So this is where we are. Okay, adenylyl cyclase converts ATP into cyclic AMP. The cyclic AMP activates protein kinase A. Protein kinase A then phosphorylates a calcium channel. The phosphorylated calcium channel then opens up, and when it opens up, you allow more calcium into the heart cell. And now this calcium is going to lead to, and we won't talk about that today, of course. This calcium is going to lead to increased contraction. Okay? And we'll talk about the exact mechanism for that in more detail later on, but I want to talk about something else first. Now, adenylyl cyclase. Adenylyl cyclase here. There it is. Adenylyl cyclase. Okay. Well, let's talk about this first. Here we have, okay, let me ask you all this question. The G stimulatory alpha, can it stay on forever? What would happen? Can you keep the G stimulatory alpha with GTP? Can you keep it in that form forever? No, you can't. Why would it be bad to keep it on? Because exactly, you'll keep making more and more cyclic AMP and your heart rate will just be high too much, and then you would eventually have a heart attack. That would be bad. Okay? Now let's go to our next member in this pathway. Cyclic AMP. Can you keep high levels of cyclic AMP all the time? No, for the same reason. So you need a way to break this cyclic AMP down to just AMP. And so what's going to happen is there is an enzyme. I don't see any room here for me to write. Let's see if we can move this over. Let's see if we can move some things. I'm going to move this over here for now. Okay. And so there's a protein that is going to convert this cyclic. It's going to convert this cyclic AMP into regular AMP, non-cyclic AMP. An enzyme. Now I'm going to tell you the name of that enzyme. Since that's a phosphoester linkage or a phosphodiester linkage, the enzyme is called phosphodiesterase. And that way you won't keep your cyclic AMP levels high all of the time. Phosphodiesterase. I guess I should write the name here. Let's put it right here. I'm going to put the name here. PDE equals phosphodiester race. So phosphodiesterase takes the cyclic AMP and breaks it down to AMP. Why do you need phosphodiesterase? Why do you need phosphodiesterase in your heart cell? Exactly. So your heart rate won't stay up all the time. You want your heart rate to go up when you need it to, but when you're finished with that stressful situation, you need phosphodiesterase to come in and convert that cyclic AMP to a non-stimulating form. The last point I want to make today. There is a chemical that you can that you take often. And what that chemical does, let's put this here. What that chemical does is it blocks phosphodiesterase. It blocks the action of phosphodiesterase. This chemical blocks the action of the phosphodiesterase, and now the phosphodiesterase can't convert the cyclic AMP to AMP, and so it keeps your heart rate elevated. Some people drink this chemical in the morning time. Caffeine, exactly. And so this is what caffeine does. Caffeine blocks phosphodiesterase. And that's what elevates your heart rate. So caffeine actually just elevates any sort of sympathetic response. It causes you to be, it can imitate a stressful situation by blocking the phosphodiesterase, keeping the cyclic AMP levels elevated. Make sense? Okay. So we're going to stop there. Are there any questions? Any questions? Yes. this should be in your textbook. Just look for phosphodiesterase.
Okay, so we're not on like a specific chapter.
No, well, the chapter that we're on now is going to be, if I say in the chapter, it'll be 32, the very last chapter. What I'm trying to do now is give you all a context for biochemistry. Why do you need to know biochemistry for medicine? And then once you understand, okay, I see this is absolutely necessary that I understand this, then we'll go back and start building our way up to it. But I want you to have the rationale in your mind so that I won't have to convince you of biochemistry's importance. Any more questions? Okay, very good. I will see you all tomorrow.